G'day, welcome back to Mathematics, the channel that is trying to help you improve your HSC, whether you like it or not. Today I'm going to take you through the bivariate data analysis topic. This is a common content area for the standard and advanced course, so hopefully this is relevant to a bunch of people who are tuned into the channel. Let's dive into the first section of this topic, which is looking at bivariate data and putting them on what we call scatter plots. Here we go. Right here we have a scatter plot. Now a scatter plot is a way of measuring bivariate data, and by bivariate I mean each point has two variables being measured. So for example, this black dot right here, this data point represents, in this case it's an anaconda that has a length of 150 centimeters and it is 2 years old. Also we have a third variable in this scatter plot actually, because we have the black dots being data points for male snakes and the white squares being for female snakes. This is taken from the 2024 HSC exam and it's a band 4 level 4 standard maths. Okay, now the actual question, once we're done reading the scatter plot and interpreting what's going on here, the question was asking us to write 3 observations about anacondas that can be made from the scatter plot with no calculations required. Okay, so having a look, what other trends are we seeing in this data in this scatter plot? Well, we can definitely see that across the age group from 0 to 10 years, the male snakes, which are the white boxes, are typically longer in length than the male snakes because they are further up on the y-axis. We can see that as time goes on, the difference in length between the two genders is increasing. So that tells us that not only are females longer, but they're also growing at a faster rate because the gap between them is widening throughout the scatter plot. We can also see that at the start, so our age 0 is going to indicate when these snakes are born, 0 years old. And from our y-axis here, we can interpret their birth weight, or their birth length, I should say. So let's make down some observations and try and get some points for this question. First one we can say is that, like we said, female anacondas typically longer than the males from this data set. And as we said, the females are typically growing at a faster rate because the gap between them is widening as we move further throughout the age groups. We can have a look at their birth lengths, looking at the y-intercept, seeing that if this is 50 and this is 100, typically the snakes are born at around 75 to 90 centimeters in length. And what else can we see? One more point to make is that if we look at the male data set, which is the black dots, when we hit around 4 to 5 years of age, from then it seems like these snakes have pretty much hit maturity, because from then onwards their length is not really increasing too drastically. So they're kind of like they hit puberty here, and now they're no longer having any more growth spurts and they've hit their sort of adult length here. Whereas for the female snakes, the white boxes, we can see throughout the 10 years, they are always constantly growing and maturing. So our last point to make is that males are reaching adulthood or maturity at around 4 years, and then the growth rate drastically slows, whereas the female anacondas are continuing to grow throughout the 10 years. So any 3 of those 4 points would have gotten you 3 marks for this question in last year's HSC, and that's how we read a scatter plot. Okay, something else we're looking for when we're analyzing scatter plots is a thing called correlation. Okay, correlation is a mathematical relationship between two variables. What that means is if one of the variables is increasing, then the other is increasing or decreasing. All right, they're having a relationship between each other. Now, correlation is actually a statistic that we can measure. It gets its own little letter, which is lowercase r. This represents correlation. And correlation can range from +1, which is a perfect positive relationship, like my relationship with my mother, and the other end of the scale is -1, and a correlation value of -1 indicates a perfectly negative relationship, like my relationship with my mother's boyfriends, #child of divorce. Okay, so here's what a +1 R value looks like. It's a perfectly straight line, and we can see that increasing one variable is directly increasing the other one. If we have an R of -1, it's the same sort of shape, but it's a perfectly negative line. So increasing one variable is strictly decreasing the other, forming a perfectly straight line on our scatter plot. Now, halfway between those two, ranging from +1 to -1, in the middle is going to be an R value of 0, and that's going to look like this, where there's no linear association, there's no pattern here. We aren't seeing that increasing one variable is changing the other one in any realistic way. So no pattern, perfectly straight line pattern, and perfectly negative straight line pattern. Now, we're not going to be seeing these 3 very often because usually correlations on scatter plots look more like these, where we're ranging between 0 and 1 or 0 and -1, depending on the strength of the relationship. So if you can see a bit of a linear trend, but the dots are pretty spread out, it indicates that you've got a weak linear association and your R value would be closer to 0 than it is to 1. If you're starting to see a pretty clear trend, it means your R value is closer to around the midpoint, which is 0.5. And then the closer that R value gets to 1, the closer these lines or these dots join together and form a line. So it's basically measuring how strong or how clear the line is from 0 to 10, okay? And 10 being plus 1. So this leads to some pretty simple and straightforward multiple choice questions occasionally in the HSC, like this one from 2017. We have 4 options and it says, which of these data sets graphed below has the largest positive correlation coefficient? Okay, let's talk about these. For this first one here, we have a perfectly straight line, but we aren't seeing an increase or a decrease in the other variable. There is no increase line or decrease line. Even though it's a perfectly straight line, it's not showing any relationship. This is equivalent to seeing like a gradient of 0 on a line. So this one would have no correlation whatsoever. Option B has perfect linear negative correlation. So this would be pretty much close to -1 in terms of its R value, but we're looking for the largest positive correlation. Now C and D are showing positive correlations because we're seeing a upwards linear trend from left to right. And as we can see, the dots in part C are forming much more of a straight line than the dots in part D. So that means C is going to be our answer for the largest positive correlation value. Similar one from 2016, the year before, we have a scatter plot shown here, and it's asking us which of these 4 options is the best approximation for the correlation value, which is the R value, in this data set. So it's definitely not going to be -1 or 1 because these would be looking like a perfectly straight line and we cannot see that. So because our dots are pretty spread out, it's a pretty weak correlation value that's going to be closer to 0 than it is to 1. So it's definitely got to be B or C. Now, are we seeing a positive or a negative linear trend? Well, from left to right, our trend we can see is trending it downwards slightly. So we are seeing a negative correlation, and that's why option B is going to get us the point for this one, not A, C, or D. Okay, so we can estimate correlation values based on scatter plots. If we want to be more precise and actually calculate this R value, we're going to need to get a calculator involved. So for this next one, I'm going to have to go and run and grab my calculator. If you have a scientific calculator nearby, please grab it and play along with me, and I'll show you how to input this data into your calculator and get it to give you the value of R to some decimal places. So we'll just pause there, I'll get my calculator, and I'll be right back. Okay, and I'm back. I've got my calculator. Now, hopefully yours is a Casio calculator as well, so it'll all be very similar to what I'm doing on the screen. This one's a bit of an older model, but it is a free emulator, so I'm not going to argue with the price tag. Okay, so let's rip into it. First thing we're going to do is put this calculator into stats mode so that we can calculate some stats. So we're going to press mode. I'm going to go option 2 for stats. Now, if we were entering a single variable data set, it'd be option 1, but because we have bivariate data, we've got to go option 2. A plus bx is the shortcut for bivariate data. So pressing 2, it's now going to give me 2 columns, an x and a y. Now for this one, I'm going to enter my heights in the x column, and then I'm going to go through and enter my foot lengths in the y column. So bear with me here. We're going to go 1, 4, 2. Actually, I'm going to type it because that's going to be way quicker. So you're typing it in and then you're pressing equals to enter in the data set. I'm going to use my keyboard because time is precious and I hate long videos. So typing them all in, da 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 da. If I make a mistake, let me know in the comments because it'll be very embarrassing, but I am rushing and impatient. 149, 181, 175. This is good content, hey. 177. Okay, entered in all my heights. Now I'm going to go across and go up to the top of the y column. And I'm going to enter in all my foot lengths. So 20, 26, 28, 26, 22, 23, 24, 29, nope, 29, 27, and 27. Okay, now my data is entered in. I want to clear the screen, but I don't want to turn off the calculator and go back to the start. So all I'm going to do is press AC, which is all clear. Did that one enter in? Let's have a look. It did. Okay, it's in now. Okay, so like I said, to clear the screen, we press AC, but now the data is stored in my calculator, ready to use. Okay, now we're going to find our stats, and the way you get them is you press Shift and 1 to get this yellow stat right here. So Shift 1 opens the stat menu. Depending on how old or new your calculator is, your options here might be a bit different to mine. But for this topic, we're looking into regression lines, which we'll talk about more later. So for me, it's option 7. It might be something different for you. So option 7 brings up these options. Option 1 and 2 are going to be relevant very soon, but for this question we want to find the correlation value, which is the 3, which gives us the lowercase r. Now I would expect there's a pretty good correlation between height and foot length, and let's see if the data agrees. R is equal to 0.94, which is a very strong correlation value because it's positive and it's very close to 1. So there is our R value. To 2 sig figs we got 0.94, and let's put that onto our answer. 0.94. Describe the strength of the relationship between height and foot length for these surveyed students. Okay, questions like that are very common in the HSC, and for your answer, all they're looking for is 2 words. The first word identifies the direction, either positive or negative, and the second word indicates the strength, weak, moderate, or strong. We are seeing a positive value, and we're seeing a value close to 1, so we are seeing a strong positive correlation in our data. And that's how you use your calculator. Moving on to the next section, we're going to do another one of these very quickly because we can also be asked to calculate a correlation value from a graph like this, as was done in 2019. So let's get that calculator back, and I'm just going to switch it on and off to get back to the start. And now I want to enter in my data. So I'm going to go mode, option 2 again, and then go back to 2 for 2 variable data. Okay, now each of these points need to be entered into my calculator, and I've got to be very careful so that all the x's line up and all the y's line up. So my first 2 x values are 136 and 138. So we'll type those in. Okay, for my third point, I've got 140. Then after that, I've got 2 points that both have an x value of 144, so I've got to enter that twice. And then my last 2 points are 146 and 148. 146, 148. Okay, beautiful. Now going across to my y column and entering my y value. So my first 2 points both had y values of 142, so they're going to get 142. My third point jumps up to 146. Oop, just hit my mic. Okay, I'm back. Okay, the fourth and fifth points have a y value of 148 and 149, and then 150, so I can just chuck those in straight away. 148, 149, 150. All right, and the last points, that goes with the 148x, is a y value of 152. Okay, 152. Okay, now like I said, we want to clear the screen, but we don't want to turn it off, so we just press AC, all clear. We go to our stats menu, shift 1. We press the option for regression lines is what these lines are called. And so option 7, option 3 for my R value, and then for this one, we get a correlation value of about 0.98. So a very, very strong correlation, and that's why all these points are pretty close to forming a positive straight line. Okay, cool, so we can put in our answer there. Oh, sorry, we're just gonna put it back on our screen, 0.98. And now part B of this question was identify the direction and strength of the linear association between height and arm span. Just like we said before, we only need 2 words here, and our 2 words are the exact same. We are seeing a strong positive linear trend. Positive value, close to 1, so strong and positive gets us the points. Okay, now for the next section of this video, or this lesson, we're going to talk about lines of best fit. So we are going to imagine a line equation that goes through the center of our data and tries to minimize the distance between the line and all the points. I'll show you what it looks like for this one. There is my line of best fit, okay? I can see I have 3 points above my line and I have 4 below, but they're all pretty close to being smack bang in the middle. Okay, now with lines of best fit, which we also call least squares regression lines, sometimes we can be asked to draw these by eye, and sometimes we can be asked to find the equation of the line. And that's why when I type into my calculator, when I have my data in before, and I pressed mode and I pressed stat, option 2 said a plus bx, because that is the equation of the regression line, which is also the line of best fit. Now, if you want to find the equation of this line, you can find that using methods that you were previously taught in this course, where you can find the gradient and the intercept of the line and then go into gradient intercept form. Or if you want, if it's more convenient, like in this question, you can find these values of a and b from your calculator and then write it down into your equation. So I'll show you how we do that. We're going to clear this screen. We're going to go back into our stats options and back into reg. And then options A and B, or 1 and 2 actually, are the 2 numbers that you need to form this equation. So A is the number that's by itself, which is your y-intercept, and B is the number that's multiplying the x, which is your gradient. So if I type in 1 and press A, it tells me that the A value, which is the y-intercept, is going to be about 23.7. Now we clear that again. We go back into reg in stats menu, And then option 2 is your B, which is your gradient. And for this one, the gradient of the line is about 0.866. So we write those down. We have our A, we have our B, we sub them into here, and now we have the equation of our least squares regression line, which is a line of best fit in the scatter plot. Okay, so that's how you do that. Now we're going to talk about how you can do that without using your calculator and just using good old-fashioned linear algebra. So we're going to switch to full screen mode for this one. So I'm just going to have to pause and come right back. Okay, and we're back. So like I said, I'm going to show you another way of finding the equation of this line, just to give you multiple different avenues for answering these questions. Using this example from the 2021 HSC, and this was a band 5 question that a lot of people really struggled with. We have the least squares regression line in our scatter plot shown by this dotted line, and for 2 marks, we want to find the equation of it. Now, if you want, you can grab your calculator like I just showed you, and you can enter in these 5 data points and then press all the buttons and get your A and get your B and write your equation just from before. Okay, that will work fine. As an alternative option, you can use this option where you know the equation of any straight line is given by y equals mx plus c. Y and x are your variables, m is your gradient, and c is your y-intercept. Okay? Now, to find your gradient, you just need to pick 2 points that the line is clearly going through to make yourself a little triangle. So I'm definitely going to start down here with this point, which is just 0, 2. That's nice and easy. Another good point would be, let's go right here. The 5 and the 18 is a nice point that the line is going exactly through. So pick some easy coordinates to read and make your life a little bit easier. Okay, using those 2 points and the line, we make ourselves a little right angle triangle, and we go for the old rise over run. The rise is how tall this triangle is, and the run is how wide this triangle is. Now, from 2 up to 18, that is a distance of 16. So the rise of the triangle from 2 to 18 is 16, and our run is just going from 0 to 5, so the run is 5. So our gradient, rise over run, is going to be 16 over 5. And if you're more comfortable using a decimal, 16 divided by 5 is 3.2. So there is our gradient, which would be one of the numbers that our calculator gave us anyway. Now, for your y-intercept, the c, where is this dotted line passing through the y-axis? Well, it's going through right here, which is at y equals 2. So our c value for our y-intercept is 2. And so these are the 2 numbers that we are putting into our equation and writing our line as y equals 3.2x plus 2. That is the equation of the regression line for 2 marks. And that is the question that a lot of people struggled with a few years ago. Okay, this question had a second part. Part B is that suppose a 6th data point was collected on a day, which had 10 hours of sunshine and then 45 bottles of lemonade sold. So our bivariate data set here is number of hours of sunshine and number of bottles of lemonade sold, maybe for a lemonade stand. Who knows? Okay, question is saying what would happen to the gradient found in part A? Okay, so every time we add a new point to our scatter plot, it's going to affect where this line is going, because the line is always trying to get as close as possible to as many points as possible. So if I'm going to add an extra point that's going to be above this line, it's going to cause this line to increase its gradient to try and reach that dot. So adding points above the line is going to increase the gradient. Adding points below the line is going to decrease the gradient. So what we're going to do is we are going to see where this line predicts an x value, which is number of hours of sunshine. We're going to see what our prediction of 10 gets us for our number of lemonade bottles sold. Okay, so what that means is if I take my equation here and I let x equals 10 for number of hours of sunshine, I'm going to get y equals 3.2 times 10, and then I'm going to add 2. This gets me an answer of 34. So this is saying that the line is predicting that when number of hours of sunshine is 10, on the line, that is going to give us a y value of 34. Now, the actual data point that we've been given that doesn't fit onto our graph here is that 10 hours gives us a y value, a number of bottles sold, of 45. Okay, so that means that 1045, the extra point being added, is going to be above our predicted point, which is 1034. That means this point will be above the line, and that means that's going to cause the line to increase its gradient to try and get closer to this point and fit the entire data set a little bit better. So gradient has to increase because the actual data point is above or higher than the predicted data points, and that's how we get 1 mark for this part B. Okay, what do we got next? We've got one more example on using regression lines. This is a really tricky one from the 2013 HSC at a band 4-5 level. It's got a few components. I think there's 4 parts, and we're going to do first 2 parts on this slide. Okay, we have data collected on the ages and heights of males aged 11 to 16 years. Before you accuse me of investigating and studying teenage boys, I'll just say this is from the HSC, not from me. All right, so send your complaints to Nessa. Okay, the scatter plot is shown here, including a line of best fit. We've got a lot of different points, and we've got our line of best fit just here. Now, because this scatter plot has a lot of points that are not very easy to read, entering these into a calculator is not going to be a viable option. We have to rely on being able to find line equations. Okay, part A, determine the gradient of the line of best fit. We can see the line of best fit here, and to use our gradient, we need to find two nice and easy points to read, make a little right angle triangle, and then do our rise over run, just like in the previous example. So why don't we just go from the start point, which is just here, and the end point up here, because they are 2 points that is very easy to read, or we could use this point here as an alternative, but it doesn't really matter where you pick your 2 points. Our triangles will give us different numbers that end up with the same answer. Okay, the fractions will simplify all down to the same thing. So using the start and end point to make a right angle triangle, and we're going to analyze the height and the width of that triangle. Now for our y values, right here is looking to me like 146 because each of these lines are going up by 2. So we have 146 here, and up the top here we have 176. So from 146 up to 176, that's a distance of 30 centimeters. And across the x-axis, or the a-axis I should say, for our ages, we're going from 11 to 16, which is a distance of 5. So calculating our gradients is going to be rise over run, which is going to be 30 divided by 5, and 30 divided by 5 gives us a gradient of 6. So this line is increasing at a rate of 6. Now part B was the band 5 part that a lot of people struggled with 12 years ago, which is explain the meaning of the gradient in the context of the data. Okay, so what does that mean? So because our line is showing the growth rate in terms of age and height for teenage males, the 6, now the significance of the gradients is the gradient is the rate of increase of your line. By that I mean every single time that this line goes across 1 unit, the line is going up by 6 units. Okay, that's what this 6 indicates. You go across 1 and you go up by 6. Now putting that concept into the context of this data, every time this line is going 1 unit to the right, that is the age increasing by 1 year. And the line is going up by 6 centimeters every time you go across 1 year. So contextualizing that, it means that that's the average growth rate per year of these teenage boys in our data set. Okay, so 1 year of growth equates to a change in height of 6 centimeters. Okay, so the males in this data set are growing 6 centimeters per year on average based on this line of best fit. Okay, finishing off with the last 2 parts, which is question C, determine the equation of the line of best fit shown. Now, this is quite a deceptive question. We know that the equation of a line, as previously stated, is y equals mx plus c. We already have the value of the m, so we know that m is equal to 6. The tricky part for this one is finding the y-intercept, okay? Yes, we could just grab our ruler and continue this line down here and see that it's hitting this axis here at about 140, sorry. Now, the issue here is that 140 is actually not the y-intercept, because if you see here, the y-axis is always going to be occurring when the value of x is 0, okay? Normally you step down from 3 to 1, 0, but our graph is only stepping down to 10, so there's still 10 more gaps to go to the left before this line actually gets to the y-intercept, which is really, really conceptual to see, okay? So if you want, you can start with this y value here of 146, and you can just step to the left 11 places, so you can go down by 6 centimeters 11 times. That will eventually get you to your true y-intercept. As an alternative option that's a little less finicky and a bit more algebraic is you can just go to your equation, because we already know half of it. We know y equals 6x plus c. We can just pick a point that this line is going through. We can take the x and the y value, we can chuck it into this equation, and then we can figure out what the value of c is that makes it work. It's a clever little workaround, and it's a good skill to know for any standard or advanced student. So I'm just going to pick this point right here, bang on the line, an a value or an x value of 15 and a y value of 170. So we're going to say when a or x is 15, the y value is 170. Putting that into my equation, I get 170 on the left, and I'm changing the x value to be 15, and now I'm trying to figure out what the plus c is that makes this equation work. Okay, so 6 times 15 is 90, and then I can just subtract 90 from both sides, and I end up with c equal to 80, and that is the y-intercept. You also could have got that by taking away 6 from 146 11 times. you would have got the same answer, but I think this is a little bit simpler for my little reptile brain. Okay, now we have our M and we have our C. We can write our equation. We can say y equals 6x plus 80. And we can make this a little better because our graph here doesn't actually have an x and a y axis. It's got an age and a height axis. So we can change this to be height equals 6 times age plus 80. Okay, a few more parts, I believe. Part D and E. This question's got 5 parts. That's a massive, massive question. Part D is use the line to predict the height of a 17-year-old male. Okay, that's not too bad because 17 is just one step to the right here. So we could just grab our ruler and extend this line one more block and we'd have a pretty good accurate prediction of 182, what looks like. Or if you want, now that we have our equation that we formed in part C, you can just very quickly use this by subbing in an age of 17 and seeing what you get for a height. So that's probably the quickest way to do it if you don't have a ruler, which everybody should if you're doing this in the HSC. Okay, 6 times 17 is something. If you add 80 to it, you get 182, and that is our predicted height on the y-axis when the x-axis goes across to 17. And the final question, why would this model not be useful for predicting the height of a 45-year-old male? All right, well, let's think about that. Every time this line is going to go one age to the right or 1 year to the right, the height is going to go up by 6 centimeters. Now, that may be accurate for a teenage boy between the ages of 11 and 16 because that's typically where you hit puberty, have a growth spurt, and you have pretty drastic changes in your height. Most people typically stop growing at around the age of 18 or 19, so this trend is not going to be applicable for age ranges outside of our data set. So this concept of taking a pattern within your data set and trying to apply it to numbers that are outside of your data set, this is called extrapolating, and sometimes it can be very inaccurate. In this case, applying data around teenage boys to make a prediction about the height of a 45-year-old male, that's obviously not going to be very accurate because people don't continue growing into their 20s, 30s, and 40s. So because this is a data point that is outside of our data set, it would not be an accurate extrapolation and would give us a very inaccurate result. Okay, that's going to do it for today's video. Hopefully that gave you a bit of a better understanding of how the bivariate data topic works and how to find line equations and use your calculator properly. Thanks so much for watching if you made it to the end, and I look forward to helping you out with your revision in future HSC videos. Goodbye for now, not forever. Good luck with your HSC.